The topic of the session is trigonometry. What is trigonometry in mathematics? What is trigonometry? Trigonometry has been derived from three different words: trigonometry. The trigonometry has trigonometry. Now, tri is 3, which is a three-sided figure, which is a triangle. We know that a three-sided figure is a triangle, and gono is angle, and metry is measure. So with these three basic words split out of trigonometry have their own individual meanings. Tri is 3, gono is angle, and metry is measure. Measure of three angles of a triangle is called trigonometry. So trigonometry split as trigonometry is measure of three sides or measure of three angles of a triangle is called trigonometry. In general, what is the purpose of trigonometry? Why did mathematicians effort in researching on identifying the topic of trigonometry? What was the need for mathematics or the branch of mathematics to come out with the purpose or the reason for identifying this topic and its significance in daily life is the biggest question out here. The purpose or the need for trigonometry. Imagine, let's come out with a small activity to understand why trigonometry is very important in daily life. Say, for example, imagine I go into the deep forest and then I just come into a place where I have a small lake bed where all water is flowing in the lake bed. So here is the lake bed, and here is all the forest complete, and even the other side there is the forest out there. So I was going on a trekking on my trip, and then I just came till here and I was halting to know how I can cross to the other side of the small lake bed or the river flowing canal to go to the other side of the forest. So I was puzzled on imagining that I can do that if I put some wooden log out here, and then this wooden log on which I'm going to crawl or walk carefully to go to the other side. To do this mathematically, I paused for a while to imagine how much of the wood or the log of wood I can put on this canal bed to go to the other side. I wanted to estimate the length of the wood log I need to put on the river flowing small canal. So this puzzled me because I couldn't exactly measure the length of the width of the canal or the width of the river flowing there by just measuring with a tape, because I cannot do that manually because for a while I don't have the log here. So how do I find the length, the width of this using the mathematics or the branch of mathematics is the biggest question when I go and stand at the bank of the river this side. So these kind of questions were big puzzles in identifying how we can successfully go to the other side of the forest. This can be done, and this is strictly possible if we know the topic of trigonometry. Trigonometry helps us in estimating this distance without actually measuring it. The power of trigonometry is to measure these distances without actually measuring with tape. Imagine I have a long tower, say it is a Qutub Minar. I have a Qutub Minar here. And then I stand here. I just stand here. And then I want to find the height of the Qutub Minar by just standing out here, which is just 5 meters away from here or 15 meters away from here. Then how do I find the height of the Qutub Minar without actually measuring with tape? It is possible using the topic of trigonometry. Trigonometry is how we introduce the concept of trigonometry, which solves many problems like finding the height of the Qutub Minar or crossing the length of the river onto the other side, by crossing to the other side of the forest by just estimating the width of the river. So all these real life puzzles or tasks can be overcome if we know the concept of trigonometry applied in real life. Let's consider a right triangle and see how the real life puzzles can be solved using trigonometry connected with right triangle. So let's see how a right triangle is connected with the trigonometry. To come with this real life example, if this is the Qutb Minar, the height of which we need to find, imagine we can convert this real life puzzle into a right angle triangle or a right triangle. If the person standing here is watching the top of the minar, then this being perpendicular clearly makes me understand that this real life problem can be converted into a right angled triangle. This being the height of the Qutb Minar, and this being the distance from the person to this, and this being the distance from the eye to the top of the minar, as can be taken. Therefore, if I take a right angled triangle with vertices A, B, and C, then there are three important factors we must know in right angled triangle. If this angle is 90, then in this case of the right angled triangle, if angle A is 90 degrees, then BC is called the hypotenuse because this is opposite to 90 degrees. The side opposite to 90 degrees will always be the longest side in a right angled triangle, and that side is called the hypotenuse, the longest side. So BC is called hypotenuse next. If I take this angle as theta, then that means the angle which the person is making with the top of the minar is theta, then the angle which the person makes will be considered as angle ACB or angle C, which is theta. So using this, we understand that any side opposite to this angle is called opposite side. This, of course, is hypotenuse, and this is called adjacent side. So these are the three sides which are very important out here, because this is called opposite side, this is called hypotenuse, and this is called adjacent side. Opposite because this side is opposite to angle theta, hypotenuse because this is opposite to 90 degrees, and finally the third side, which is this, is called adjacent side. This is just adjacent to the angle. So BC is hypotenuse, AB is opposite side, and AC is adjacent side. Is how we get each of the sides, hypotenuse, opposite, and adjacent, this being the angle. Therefore, if suppose I have a triangle with angle out here, then in this case, this being 90, I understand that this is hypotenuse, usually hypotenuse denoted with H, and opposite side denoted by O, and adjacent side denoted by A, will have its opposite side here and adjacent here. The opposite side comes here because the angle theta is here, and opposite to that will be O. Is how we get. Suppose I have a triangle, say, so this is 90 and this is theta, then clearly angle 90 degrees opposite to that will be hypotenuse, opposite to theta is O, and this is adjacent. Is how we understand the different right angle triangles taken in different forms, finally giving us the opposite side, adjacent side, and hypotenuse for a right angled triangle. Trigonometric ratios is one of the most important factor of trigonometry. The origin of trigonometry has finally led to trigonometric ratios, which help us in solving the previously discussed puzzles. The main intention of trigonometric ratios is to solve some of the mysteries, like finding the height of the Qutb Minar or crossing the river or finding the width of the river flowing opposite to go to the opposite side of the forest. So how do we see? Let's see how trigonometric ratios have come into existence. What is the purpose for inventing the trigonometric ratios, or we can call this as origin of trigonometric ratios. So let's see how it comes into existence, of course connected with right angled triangles. So in this case, let me imagine a right angled triangle which is, say, quite very small out here. I take a very small right angled triangle, in this case right angled at this, and this being theta. So if this is theta and this is right angled triangle, then obviously we know that the side opposite to right angle is hypotenuse and the side opposite to theta is opposite, and obviously the third side is adjacent, is what we understand in this triangle 1. So this is triangle 1. Similarly, I take the triangle 2. So in this case, let me take a little bigger triangle, say, in this case, same angle theta. I do not change the angle theta, which is for this. The same angle is maintained out here, and then this is opposite, this is hypotenuse, and this is adjacent. Next, I consider the third triangle, the triangle 3, which is quite big. This is the triangle which is bigger than this and more bigger than this, and here I take the angle theta. Now let's identify H, O and A. This is H, this is O, and this is A. Now since each of them are with different dimensions, I take this O1, H1, A1, O2, H2, A2, and O3, H3, A3, because the three sides are different. Each of the respective three sides, H, O and A, are different. So for triangle 1, my hypotenuse is denoted with H1, opposite with O1, and adjacent side with A1. But interestingly, for each of them, the angle is same. This is a very important note to be made, that here one of the angle theta is same, but each of the sides are with different dimensions. Smaller triangle, medium triangle, and a bigger triangle. So here theta is same, it is not changed. So let's see what interesting factors come into existence in the trigonometric ratios. So mathematicians started identifying for triangle 1, say I take for triangle 1, I just divide opposite side with hypotenuse, and then for triangle 2, I just divide the opposite side with H2, and for triangle 3, I divide opposite side with hypotenuse. Interestingly, mathematicians have come out that for triangle 1, where the theta is same, O1 by H1 gave an approximate k value. Say it is some k. When divided, it gave some decimal value which was denoted with some k. Similarly, for triangle 2, with the same angle theta, when this was divided with this, the measurement of O2 divided with H2 has given the similar approximate value of k. It gave the same k as obtained in triangle 1. Further, when this side was divided with this side approximately with the same angle theta, this dimension by this dimension of the third triangle also gave an approximate value of k. That means each of the triangles had k which was approximately same, but not exactly equal, but with minute error in the value of k. Therefore, this made mathematicians understand on the common factor between each of the triangles where one of the angle is same. In a right angle triangle where theta is same, then there was some relation between opposite side and hypotenuse of each of the triangles where all of them were k, etc. So the mathematicians started calling that opposite by hypotenuse as sine theta. The purpose of inventing this common thing was denoted with opposite side by hypotenuse, and it was defined as sine theta. The word sine, which stands for sine of theta, was taken as the root. So sine theta was the value given for opposite side divided by hypotenuse. So whatever k I get here is now called sine theta. When I divide the opposite side by hypotenuse, the value I obtain is called sine theta. And that is for any triangle with angle theta. I take a big size of a triangle as huge as the sky and take the angle theta to be same, then opposite side by hypotenuse of that triangle will be same as opposite side by hypotenuse of this smaller triangle. That's how we conclude through the opposite by hypotenuse. Similarly, as we connected opposite and hypotenuse, there were also similar comparisons made from adjacent by hypotenuse. So let's see what interesting facts have come through adjacent and hypotenuse connected through the ratio. Next comes connecting adjacent and hypotenuse. So for triangle 1, triangle 2 and triangle 3, I have adjacent by hypotenuse is approximately equal to adjacent by hypotenuse approximately equal to adjacent by hypotenuse, which was denoted with some k. This was also true for adjacent divided with hypotenuse, just like opposite with hypotenuse. So whatever adjacent length divided by hypotenuse, and this by this and this by this of any size triangle, provided theta is same, has given me all equal values, and that equal value was denoted with cosine theta. Cosine theta is what it is denoted with. So this value has been denoted with cosine theta, or cos theta is called adjacent by hypotenuse, is what has been derived as the formula for trigonometric ratio. One of the trigonometric ratios is cosine theta or cos theta is adjacent by hypotenuse. Now lastly, let's see the comparison between opposite side and adjacent. We have compared between OH, HA. Now comes the turn on comparing between A and O. So let's see what is the interesting conclusion made out there by the mathematicians. Now let's see the relation between opposite and adjacent side, where for triangle 1, triangle 2 and triangle 3, I have opposite by adjacent for triangle 1 is also equally, approximately equal to the opposite by adjacent of the triangle 2. Similarly, if we take the opposite side with adjacent side for triangle 1 is approximately equal to O2 by A2, approximately equal to O3 by A3, which is some constant k. This also made the mathematicians come out with tangent theta or tan theta equals O by A. Is how we understand the trigonometric ratios. So these are the three trigonometric ratios. Now that we have connected A with H, H with O, and O with A, we have three trigonometric ratios invented by mathematicians for a right angle triangle using this purpose of same angle theta. So therefore, let's recap with how the trigonometric ratios are framed into formulae. Therefore, for three trigonometric ratios which we have identified for a right angle triangle are, for this right angle triangle, if this is theta, then this is opposite side and the hypotenuse and the adjacent side. Then the first trigonometric ratio, we call it as sine theta, is opposite by hypotenuse, And the second trigonometric ratio, which is called cos theta or cosine theta, is adjacent by hypotenuse, and the third, which is tan theta or tangent theta, is opposite by adjacent, are the three trigonometric ratios identified for a right angled triangle. Is how we understand sine, cos and tan, the three trigonometric ratios in order. Now let's see the reverse trigonometric ratios or reciprocal trigonometric ratios. It's very simple that we have already discussed for a right angled triangle where this is theta and this is right angle, this is hypotenuse, opposite and adjacent. We had three trigonometric ratios, sine theta, cos theta and tangent theta, as opposite by hypotenuse, adjacent by hypotenuse, opposite by adjacent. Now, these three trigonometric ratios, which are called the standard trigonometric ratios, have led to the reverse trigonometric ratios, which are cosecant theta, or we can call this even as cosec theta, equals 1 by sine theta. So reciprocal of sine is called cosecant theta, and the reciprocal of this would definitely make this reverse O by H to H by O. Therefore, hypotenuse by opposite is referred as cosecant theta, and opposite by hypotenuse is referred as sine theta. To start with this. Then secondly, my cos theta when reversed gives me secant theta or sec theta. The short form of secant theta is sec theta, and this is nothing but reciprocal of cos, which we refer. Reciprocal of cos is secant, and then that is h by a, because a by h is cos. I get this as hypotenuse by adjacent. Similarly, when I take the tan, the reciprocal of tangent theta is called cotangent theta. Therefore, this is called cotangent theta, written in the short form as cot theta, so that this reduces to the reciprocal of tan. So the reciprocal trigonometric ratios have their own formulae, where cosecant is 1 by sine, secant is 1 by cos, and cot or cotangent is 1 by tan. Therefore, tan theta being O by A will be A by O, that is adjacent by opposite, is what we get for the reciprocal trigonometric ratios taken as a formula. Reverse trigonometric ratios are cosecant, secant, and cot. And the standard trigonometric ratios are sine, cos, and tan, have their own respective formulae with their own definitions. Now let's see some practice problems on connecting the trigonometric ratios with the right angled triangle. That is, I give a right angled triangle, and using the right angled triangle, we need to find the trigonometric ratios. Let's see how we can do that. Before doing the problem, let's identify that there are 6 trigonometric ratios which we have discussed in the session. Sine theta, cos theta, tan theta, cosecant theta, secant theta, cot theta are the 6 trigonometric ratios which we are going to find using the given problem. Now here, tan A is 3 over 4, then I have to find all other trigonometric ratios, that is sine, cos, cosecant, secant, and cot, because tan is already given. So with the trigonometric ratio, I try to use the right angled triangle to find the other trigonometric ratios with the respective formulae as discussed in the previous session. So let's draw a right angle triangle connecting the trigonometric ratios. So this is a right angle triangle. Say the angle is A out here, because the angle is not theta, it's A. I take the angle A out here. Therefore, I take the trigonometric ratio with angle A, where one of my trigonometric ratio is given as tan A equals 3/4. But since the trigonometric ratio 3/4 is opposite by adjacent using the formula, therefore my opposite is 3 and my adjacent is 4. But because this is in fraction, I don't know what is the common multiple divided for both numerator and denominator. Therefore, opposite by adjacent equal to 3/4 implies my opposite side is 3k and my adjacent side is 4k for k belonging to z. Of course, z plus for k belonging to z. It can be negative. So for any integer k, the opposite side is 3 times of the multiple constant k, and adjacent is 4 times of k, is what we get. It can be even r. K belongs to z, or all the real numbers which come into existence except 0. All non-zero real numbers is what we consider here. Therefore, for k belonging to all real numbers except 0, I have opposite side is 3k and my adjacent side is 4k, so that my opposite side is 3k and adjacent side is 4k is what I get. Now from this, how do I find the hypotenuse? How do I get the hypotenuse is the biggest question. Now here we use the Pythagoras theorem to find h. That is, by Pythagoras theorem, hypotenuse square is opposite square plus adjacent square. But why is the need to find the hypotenuse? Because the question is to find all other trigonometric ratios. To start with sine theta, which is opposite by hypotenuse, I need the hypotenuse in the denominator of sine theta in order to find the trigonometric ratio sine. Therefore, we need each of opposite, adjacent and hypotenuse to find all other trigonometric ratios. Therefore, by using Pythagoras theorem, we extract h. That implies this gives me hypotenuse square is opposite square, which is 3k whole square, plus adjacent square, which is 4k whole square, which on further simplification gives 9k square plus 16k square, that is 25k square, is h square. That implies my h is plus or minus root 25k square, that is plus or minus 5k, but I don't take, assuming k is positive, for k greater than 0, I assume hypotenuse cannot be negative, so I take 5k. Because I don't take the negative value, because lengths are always positive. Therefore, hypotenuse is 5k, and coming to the opposite, we already know that the opposite is 3k and adjacent is 4k. So this is 3k and adjacent is 4k. Now these three values we utilize in finding the all other trigonometric ratios. Let's see how we can find each of the trigonometric ratio using h, o and a. Therefore, we have the opposite side, which is 3k, and adjacent side, which is 4k, and hypotenuse, which is 5k, found recently using the Pythagoras theorem. Now using this, I have to find each of the trigonometric ratios. To start with sine A, which is opposite by hypotenuse, is what we have as the formula for sine theta. Now what is the opposite side? Clearly I have this as 3k, so I substitute this as 3k by hypotenuse, which is 5k. And this can be cancelled because k is not equal to 0. Therefore, since k is not equal to 0, I can cancel this and I get sine A as 3 over 5. So this is one of the trigonometric ratio which is obtained using the formula for sine theta. Let's find for cos. Cos A is given by adjacent by hypotenuse, where my adjacent is 4k and my hypotenuse is 5k. Cancelling this, I get 4 over 5 because k is not equal to 0. So we get cos A as 4 over 5. Similarly, tan A is already known. So once I know sine, cos and tan, I can easily find cosecant, secant and cot. So let's see how we can find cosecant, secant and cot using sine, cos and tan.